然后为什么有这个区别？如果你们看电视剧的话，美国电视剧都是从这样子开始的 ，previously， right？ That's okay。我们说，这是我们开始的做的是Euclidean geometry，right？ 然后这里面最重要的一个 axiom 就是 parallel axiom，right？ 因为就是这个和这个projective geometry 最大的区别就是这里我们每一个直线都会有一个平衡线 whatever and here至少如果不是一样的话OK 那么左边我们问的问题是什么样的两边其实都是我们可以都在一个 plane we do plane geometry 我们都在一个 plane 上做然后呢我们都是这里面有几个点然后我们再算这里面的properties OK 两边都是这样做 OK 都可以都是个 R2 那么可是这问的问题不一样为什么So what kind of questions does make sense in Euclidean geometry, but not in projective geometry? Have you an idea? No, just if you are doing Euclidean geometry with all the axioms we talked about, what is a well-defined question? What is even does make sense? Okay, for example, let me put it this way. Let me just example. I have a plane. Okay, I compute the coordinate of this point. Actually, that doesn't make sense. Why? I can of course compute where a point lies.
This one is just like class of points.
Yeah, so it's like all the points I compute here. I couldn't move it to somewhere else, but my shape will not change, right? So kind of. Computing some coordinates seems not to be a geometric question because, it's only in relationship with other points that certain properties make sense, right? So if you are considering triangle, it doesn't matter whether it's here or there, right? It's the same geometry.
Just like a circle, it doesn't make sense.
有意义的意思 Makes sense. So actually, circle does make sense. Well, if you have a center, as an object. But of course, this circle and that circle somehow is the same geometrically, if it has the same radius, right? So these kind of questions. So now, projective geometry is different because, you see, why are we considering projective geometry? Because I have an object like a cube. And I project it to some screen, right? Now, that can look whatever. Now, I have the same object, and I have a different screen. Now, my projection here will change. Now, it might be a square in the beginning. It might be a rectangle. But it's still the same object originally, so they actually should be considered the same. So now, what property stays the same?
Line?
What is a line?
Just, I think, there's a plane that is image in that series with the line.
Yes. So, projective line. How many points determine a projective line?
2.
Why? So, first, what is a projective line? The answer was a plane is a projective line, a plane in R3. Yeah? Well, through the origin in R3 is a line, projective line. Okay, and now the question is, how many points determine that line? What do you think? Why do you? No. What determines a plane? How many points do you need for a plane? Well, you need 3 points for a plane. That's true.
But there's also this point because it's through the original point.
Exactly. So we have 1 point already. Yeah.
Yes.
So we only need 2 points for that plane. Okay. That's right. Okay. So a plane in R3 gives me a line. So how does that look? Right? We can play the same game as last time, right? We have just 2 coordinates, x and y. I sometimes write it this way, sometimes write it this way, depending on how much space I want to use. Okay? Okay. I can always, any plane, I can just write it this way, right? Some way or other. And I say xy is the same as
there exists lambda in R cross such that
lambda is enough because those are if you leave 0 out, then it's fine.
such that x equals lambda y held.
Exactly. So now what is this? So now you're saying I have a point. This is my 0. Any point defines a line, right? And plus and minus define the same line, right?
Yes.
So I have a whole circle worth of possible directions with opposite sides just attached,
Yes.
which is still a circle.
That's right.
Okay? So it's
Yes, that's right.
okay?
This is S1.
So my projective line is question. Just a circle. Let me just write circle.
Yes, it's a circle. It's homomorphism to F2. You have learned in your topology.
It doesn't matter. Yeah. Okay? 每一个方向，你看，因为这是每一个方向都有加减，都是一个line, right? You can just choose lambda to play. 所以其实这两个是一个点。
一个圆把它的所有对近点都给粘起来。
可你因为这个 dimensional reasons， 你把这边连到一起的话，还是一个圈儿。No orientational problems.
Yes, that's right.
So the difference between a projective line and a Euclidean line is that this thing here is a circle, while a Euclidean line is just a line, right?
Yes.
Has 1 point more because you put it together at the infinity, okay? So what can you ask on the Euclidean side? You can ask for distances and angles, right?
Most of them have no well-defined projective geometry.
It's not well defined. No, because when you are standing here for your cube and you have your screen here, you just put the screen slightly farther away, And that cube, which was this size, is now this size.
Yeah.
Right? It would be bigger if the screen is good.
Using the lambda as 1.
Yeah.
So distances are not well defined. They should just
Yes. Exactly.
come from our screen.
Yes. Angles are also not well defined because you can just move the plane like this, and then your projection suddenly gets a shear, right?
Yeah.
So there's no angles and no. So the question is now, what is something that is well defined in projective geometry? Well, lines are you can do. What else? What is a projective circle? What would be a circle? What do you need to define a circle? Segments. And what are the same? What are equivalents for segments? The distance, right? But then distances are not well defined, so we cannot really define a circle in the sense, right? Doesn't make sense because we need a radius, right? The distance between this here. What is this? The radius here, and that is actually a number which measures the distance between these 2 points. And now we cannot measure it anymore. Plane does make sense? Yes. We can do lines, and whenever lines intersect, we can say, well, they're lying on the same line, but not far more. And it's actually very difficult to understand. I mean, it's difficult to come up with something that is really invariant under projective geometry because so much things change, right? Okay. So now, how to attack such a problem? What remains the same in projective geometry? What do you think? How to ask such a how would you attack such a problem? So maybe some questions first. A different question, okay? What would be a map? What is a map from my plane, so RP2 or whatever, or let me say RP1, so the circle here, to RP1, meaning the projective line, the line, I'm talking the circle, preserving the projective structure. So what does it mean, even? What is a map from my S1 to S1, circle to circle, so that this remains the same? What does?
That is homomorphism, where for example, you can rotate the circle.
Yes, we can rotate the circle. Is there more?
Yes, for example, to reflect the circle.
Is there more? Is there more?
The more, I think all the isomorphism from S2, the S1 to S1 is just those kind of things, or the set of those things. Because this. I remember that
How much? How many freedoms do you have? How many dimensions do you have?
one.
重要是中文 ，OK， 就是说你从 S1， 到这个圆儿，然后保持这个 structure， 就是说，如果你有两个点儿啊，就是 like this， 那这两个必须要 map onto the same point, right? Because otherwise it would not make sense because this is the same line.
I think so that this gives a map. So this map is continuous.
Yes, but how many dimensions do you have?
One.
One.
Because,
One.
Because S1 is dimensional one. It's one dimensional. So you mean that map?
Yeah. So how do you identify that? So instead of considering this map, one could also consider a map on R2.
Oh, yes, that's right.
That's right. Because that makes sense. So when you have a map, so the other question would be, so what is a map first? How many points? 6.
Okay.
Meaning?
I got it.
Meaning, when I know the value of 1 point,
Two
how many different maps do you have? When I know the value of 2 different points, how many maps do I have? When I know 3, and so on.
2 points fixed that map.
Why?
Distinct, I mean.
Yeah, sure. Why?
Because if it's presenting the projective structure, then it should be continuous. It's just like a matrix.
Not everything is metrics. Okay.
So is that also correct?
Every answer is correct as long as you can prove it. I'm not telling you the answer. Otherwise, it's or whether it's correct or not, because look, we have something in R2, so on the plane. Okay, we have some object here on the plane, and we want to project it onto the line. That's what this is doing. Okay, what kind of different options do I have to project this object onto a line? For example, I could sit here, right, and I project my object onto the line. What I do is I would have lines going through this, and these are the endpoints of my projections, right? Yeah. The same, if you have 2 lines like this, I would map this line to this line through. Well, if I sit here, then my projection would go this way. So this point will be mapped to this point mapped to this point mapped to that. These are all projective lines, if you like. And the question is, how many different maps of that kind are there? That's the same question as to say, how many maps from S1 to S1 are there that possess that projective structure? Does it change your answer or not? So what kind of choices do you have to do these type of maps? 就是说这是我的一个 S1， 因为这infinity is also on the line 呀，我画成这个样子，然后这另外一个 line， 然后我把这个 map 到这个上去，我就说我就是 that's my observer， 就然后从这儿发这个直线，然后这个点就会 map 到这个点。这个点 map 到这个点 and then what I obtain is a map from this line to this line.
I think it's only 1 point. But if you have 1 point, you can know that what is the points that the line comes. So
1 point. Well, I can sit here. So if I sit here, I can find a map between these two lines by doing this. If I sit here, I would do differently, a different map. This point and this point would be a different map, right? So now the question is, how many freedoms do you have to make such a map? These kind of maps. And how to write it out properly. And sometimes it's easier to go 1 dimension higher because that's what you are doing, right? So what are maps from R2 to R2 that preserves the lines?
So that this F2 from R2 to R2, such as FC times H to C times H.
Yeah? How many maps? What are those maps? Huh?
就是它是让它点对点，那就有在中间找个点，这样让它这样对应。
这是一个方式，
那在外头找个点让它切一下
也行，对。
反正就是都是公切。
对，然后的问题是有多少个 freedom， 你可以选多少个way， 就是说
有多少方法？
有多少方法？对。有多少选择？有什么选择？
不是那个1维的摄影平面，他自己讲那个1维的摄影平面，不是2维的摄影平面。
We can go. First, I mean through 0, yeah? Huh? You know? Hmm?
是不是只需要验证它这个线性映射？就是说，对于 A 和 B， 然后F A 加 B 等于 F。
对，那这个是。
然后还有 F K 贝塔 A。我的俄罗斯党还有一个巨大的。
对。
俄罗斯党。
那 what are those maps？ 怎么样写？有多少个 freedom？
就一个，因为它是形如
这是从哪儿到哪儿的？对，你的 f， 你的 f 是从哪儿到哪儿的？
就是 x 这个，就是因为它这个二维的一张眼二，
从哪儿移到哪儿的？你的说呀？
那如果是这样的话，那怎么只有一个呢？
为什么只有一个呢？怎么可能只有一个？但是问题是有很多，但是很多不是对呀，就 C 为啥？
这个的话，我还是没有特别理解他到底在问什么，是问我们一个圆到另外一个圆的映射，还是说是？
也是，就是很多种问这个问题的方法，一个就是从圆到圆的一个 map，right？ 如果你把这个圆放在以为在这个 R2 里面，然后呢，这个对面的这个点要 map 到一个也是对面的点，就是这种。OK，that's one way to formalize。第二种说的话就是你从 R2 到 R2， 就是 plane to plane， 然后呢每一个直线是 map 到另外一个一样的直线，就是说你知道这一个点放到是到哪，然后另外的其他都是就是对那个 lines maps to lines right that's the point， 就是直线是在这个 map 上面是到这个直线上的。
So if we consider the R2, then it's linear, right?
Yes.
And
How many freedom do I have in the
because it's linear, and it has an f, for example, f R2 to R2. Because it's linear and because this needs to be well defined.
Yes.
If you express this, then so f0 will be 0.
Yes.
So there will be another two distinct points there.
Yes. But how to write it first of all? And how many freedoms do I have?
But if you do like so you know how the f in wait, I think
How do you write a linear map from R2 to R2?
f can be
那个 O 是原点。
0对，就是0点，原点。
0点。
对。
这个题的话是问我们是找出来一个方法，另外有几种方法？
两个都是。
一种也可以。先找出来一个方法。
对，先找一个。
对，找有几个方法。
对。
So f is all invertible to that and so but many of them have the same are the same for becoming these. And you finally get that the circle will have only two kinds of things. If
What is write down f? Give me an example of f, even with numbers.
example,
Give me a number.
Okay.
Numbers.
F2 from okay.
也可以。
For
Yes,
example,
that
for
will work.
instance, F R2 to R2 and XY to some A, B, C, D and XY.
Yes.
Such that AD minus BC is not equal to 0. And all of these in R2 it looks like if this one is bigger than 0, then it just does rotate. If it's less than 0, then it's a reflection and a rotate. So
How many freedoms do I have though?
so the freedom, you have two choices rather than you can just rotate it or you get a reflection.
Yeah,
then
sure.
rotate.
That's not too. But how many points do I have that?
There's a
How many freedom do I have? How many real freedom do I have?
this one, you mean?
Yes. How many?
But
How many freedoms do I have? How many different maps can I write down with your ABCD there? Not but.
They are all ABCD in R4 such that this.
Yes. So how many freedom do I still have? How many dimensions would the solution be?
That's just two distinct. The freedom is 1 not 2, and another in 2, but this
Yeah, and how many is it?
always really too close.
Yeah, but how? So give me a number. 1, 2, 3, 4, 5, 6.
You need 2 to
Okay. So map from R2 to R2 is a linear thing. A, B, C, D,
such that AD
such that AD
minus BC
minus BC non-zero.
is
But, okay, so A, B, C, D are real numbers.
yes, a real number.
So it's actually 4 choices.
Yes,
It's 4 choices.
about two choices in R2. I think.
No, it's 4 choices. 4 choices of numbers.
Yes.
4, yeah? And then you have one relation because you can, when you have the thing equals 1 and the thing, oops, lambda, it's actually the same map
Yes,
in R2. So you have one condition.
or -1.
Yeah, it's the same map as well, which is just, yeah. You have one condition, 4 numbers, so altogether you have 3 freedom.
Oh, yes.
That's 4 minus 1 is 3. Okay? What does it mean? Let me just explain first what that means. What does this mean? That means my point 1, 0,
Yes.
this point here, is mapped to the point
AB.
AB. CD means my point 0, 1, this one here, is mapped to
0, 1, 2.
CD. And of course, this cannot, with this AD minus BC is non-zero, means that these 2 vectors here, which are some coordinates, they have some area.
Yes.
They're not
The
together.
area is AB minus
Yeah.
BC, where the determinant.
Okay. So now when I do this thing to my R2 vector, right? I do this thing to my R2 vector x, y. What I get is, that's how you compute it, ax plus cy, bx plus dy. So this is my new point, because when I have 1, 0, I have exactly AB. 0, 1 is CD. And then you have a linear just combination of those. That's this one. So now when you do that thing in RP1, so I want to identify this thing with a line. How to do that? With an R. Well, this thing is mapped to, assuming this here is non-zero, to ax plus cy over bx plus dy. Okay? So the map, right? Well, you can maybe do this, right? Because we can, assuming y is non-zero, then the map is basically x maps to ax plus c, bx plus d. Why I'm doing that? Because every line, x, y, if y is non-zero, I can always scale it to x over y, 1,
Yes, that's right.
right?
Yeah.
So I just take this line and see what my map does, and it's exactly this one. So you see it's slightly more than your linear map, which would be only this one.
Yeah.
It's slightly more. You can map, what is the difference? You can map infinity to some finite point. Whilst when you have a linear map, infinity stays always infinity.
Yes.
Okay? So now, how many points do you need?
Oh yes, point.
How many points do you need to fix that map? You need, as I said, this is 4 different numbers minus 1 relation. 3. Because you have 3 variables you need to solve, right? When you have a linear map, then you need just to fix 2 points, because 2 points fixes a line. So if you know the 2 points, you know a line, right? But the problem here with the projective thing is you still have infinity. That might end up in 0. or at some finite points, we need 3 points, okay, to fix actually this line. Okay. So now, the next step, we're still trying to answer what is preserved under in projective geometry, right? So now, the difference now is, before we needed 2 points to fix a line, or fix a linear transformation, yeah? Now we need 3. So before, we could ask the question, when you have 2 points, right? When is a third point lie on the same line, right? Now we need to know when will a 4th point lie on the same line as the previous 3 points.
Oh yeah.
Right? Or let me, okay. A little bit of applied linear algebra. Okay. What are relations between 4 points? Before, right, we had 2, it would fix the line, and then we had distances of the third point to each of these 2 points, basically, right? Now we have 3 points that will fix my projective transformation, right, to any line. Now the question is, when I have a 4th point, what kind of property would that 4th point have? Okay, and the answer, I'm not going to tell you, but just think about the following problem. We need to normalize 3 points. How can we? And then add a 4th one. So how to normalize 3 points? And then we can go on higher dimensions, but not first on line. Yeah? We have 3 points. How to align in projective geometry can also still be identified with R, right? Well, basically R together with infinity, because that's a circle. Right? Now, how to normalize 3 points? Oh, by the way, just saying, this A, B, C, D, we could just choose the determinant of thing to be 1, and then we have actually the group acting on this is called SL2R, yeah? Which is well. That's why you are considering. That's why you are considering that. So it appears very naturally. 只是个名字。
中文是什么
SL2R, I don't know， 就是这样的吧，也是这样写的，只是这个名字，就是说，这个 matrix 加上这个 det equals 1。S 这个意思就是 determinant， 就是 determinant means the area of these two vectors AB and CD,
肯定看到过呀。
the area is 1.
你记不记得以前有一个 SL2Z？
我记得。
数论课上讲的。
Yeah,
Yeah.
the same, just with the difference. Of course, you have real numbers instead of integers. It's this. The usefulness of this is actually the same because it preserves the line, and then you can, it's basically from hyperbolic geometry. But we'll get to that later. Okay. So now, when I have a line, I want to fix 3 points on it. Okay. I claim it's possible if you have any arbitrary 3 points on RP1, then I can choose this one to be 0, this one to be 1, and this one to be infinity. How to prove that?
RPY
就是projective line， 就是说这之前说的这个只是个名字。我们之前这个就是 x y， 然后如果就是说 RP1 其实的意思就是一个 circle， 是个圈 S1， 或者是我们也说这个是个 S1， 一维，这一的意思，这个一是一维，因为这只是个 line。Only one dimension. R 的原因，因为我们 x and y 都是 R， 然后 P for projective。投影的意思。
是3D 的。Is it 3D 的
Which one? No, RP1 is one-dimensional. That's why it's only one here. So this is the dimension of your space. So you have RP2, which means that my dimension of the space is 2, meaning that I'm on a plane. This one just means I'm on a line. That's why it's one-dimensional. Okay, so always that's how, and the coefficients are in R, so I do R projective 1. That's always a count. It's a line, it's a circle. A circle is one-dimensional. That's a line.
那现在二维的就是二维的呀，它忘概念了。
我没说它是2维。
你说它不是1维？
现在2维。
诡辩，辩论。
你说什么？它现在二维的就是二维的。
看来一现在4维的，那就是3维的东西。对，看来一是2维的。看来一。
Klein bottle？ 哦，对，是2维的，对，那是 RP2， 对。
我什么时候它是2维的了？
原来不是1维的。
狡辩，
可是我听以为我是
狡辩，
第一
一张
说错，
伪。
第一说错。
No problem.
啊，嵌入的定义。
Okay.
嵌入的定义。错。
来，我
So again, how to do that? Guys, how to do that? Ever, you need to compute something properly. Yeah? How to do that?
找 P 票是33个点，这3个点。
随便3个点，对，随便在这里面随便3个点，然后然后有一个这样子一个 map，OK， 把它map 到0、1和 infinity。OK，that's the claim. And then I tell you what exactly I want to do with that. Huh?
老师，你要让我们干什么？
就你找一个 map 从这儿到这儿，随便什么 P1、P2、P3。
就是说，对于任意3个点找一个映射，使它映射到0、1和无穷上。
对。然后为什么这是只有一个？
就证明这个任意3个点，它映射到
对，
0、1
都可以。
的话，它只有一种映射。
一种映射到0、1 infinity。对。
map 不是映射的。
map
不是映射的意思。
什么？那哦，对。我不一定知道中说什么。
持续为什么做起来
？Applied linear algebra. How to start? Do you know how to start? No? Okay. You don't know how to start? You know how to start or don't know how to start? 啊，这个点是怎么写的？这个点是怎么写的？ So normally P1 is something like x, y,
x1, y1,
P2,
x2, y2, p3, x4.
well, they should be distinct, yeah? 就是说，如果其中一个，至少最多其中一个是 y 是0，是吧？就 assume 如果有一个是 y 等于0的话，那么这个已经是 OK， 所以其实所以就是说我们可以well, we can assume none of them is infinity, right?
老师跟解释一下。那个为什么 y3 会有0啊？还有什么？
你这个 R2 里面。是吧？然后我们说 x y 等是和这个是一样的。
对。
Right？ 然后我们选这个lambda 等于这个。如果 y 不是0的话，那么 x y 就是说可以选成这个。然后呢，我们就把这个 map 到这儿去。可是如果 y 是0的话，那就这里就是这个就等于是 infinity。Okay, so that's how you identify RP1 with R, right?
So if x1 equals 0, then p1 is 0?
Yes.
Okay, then the other one should be perfectly 1.
Okay.
So maybe R.
So when you have a map, so because if this is my point, this is 0, this is x, y, right? If that's x, y, this is my 0, then the whole line here is given by some s times x, y. Right? Do you know that? So just for some s in R. Okay, for s equals 1, I have this point. When s equals 0, I have 0. And then there's somewhere in between. Now I can choose s, arbitrary, because that's every point of this is the same point in my projective space. So I can just choose S to be 1 over Y. It's one possible choice, right? So it's somewhere here. I don't know, but it's just if Y is non-zero.
Yeah.
Okay. So now, when I do that, then my point here, instead of 2 coordinates, I only need 1, because the second one is 1 anyway, and this first one is 1x over y.
Yeah, but usually just add the infinity point.
And then you can just say, well, then this point already, this here, gives me which point that is, because I just write, whenever I have an x in R, I can just write x1, and I get my point in R2 as well, right? I thought you had Grassmannians. Didn't you have Grassmannians?
Yeah.
Grassmannians?
Yeah.
你们不是说你们学过吗？
Yes. 臭头人是什么？哦，yes。本来光
不是说学过的吗？
Yes.
然后学了跟没学一样。
And I found it in this book.
我这个没有尴尬。
Well, if you have Grassmannians, then this one is the easiest possible case. Okay?
没有听懂，
这是最简单的，
然后并没有听懂，
没有听懂。好，可以。可是我们从这儿开始。
然后也说了不会考，
啊
也说了不会考他，所以不弄出。
No.
弄他。
Okay. Now you're reading Grassmannians. Maybe you should solve this problem first. Okay. So let me.
So you mean that we should find out mapping?
The map from the arbitrary 3 points in RP1 to 0, 1, and infinity.
So for given P1, P2.
Given P1, P2, P3
So
arbitrary.
Map from RP1 to RP1 such that
It maps
to 0.
1 and infinity.
Okay, I got it.
Okay?
I actually understand.
"听懂那个问题是学习的一部分。
不是。上课都连题都看不懂，非常的悲催。
不是，这真的就是问问题是最重要的。问什么样子的问题，有意义也是很重要的。所以不是学的内容重要，而是学会你们学了的东西之后，应该是问什么样子的问题。Let me see. Yes, that's your goal, but then you have P1 and P2, P3 arbitrary.
Is this your goal?
Oh.
那你 okay, using a projective transformation, yeah?
I think there's a goal finding a map, but
So P1, P2, P3 arbitrary. Find a projective transformation mapping P1 to 0, P2 to 1, and P3 to infinity. And you're right, that is actually corresponds to
one map in RP2
that is that's correct. Okay? So now how to compute this map?
I got it. Map.
What's the problem?
就我说是要找一个映射，
嗯
要让它变这些。
对对，然后那个 map 是什么样的？ So our map, so this basically, I wrote down this one, x1, y1, x2, y2, and this is x3, y3, right? 然后呢，我们需要的是 A, B, C, D, right? That's my map.
然后如果要应成01的话，它那y30比应得等于0了。
Such
Oh,
that,
I get it.
yeah?
Y2.
还是学会用左手写字了。Yes, exactly.
I should write this. I'm lazy to write too.
Yeah, that's fine.
And this gives uniquely
No.
A, B, C, D. SL to
How can that give uniquely?
because you can write down this as B equals 1 minus AX over Y, and D equals 1 minus DX over Y. And by using these, because this Y is not X and Y is not 0. In this case, we should consider C. Okay, C, and C equals A minus 1 over B.
Yes, but then A is not determined, yeah?
Yes, but you can drift this B.
No.
This is.
You have 3 equations for
Yes.
4 variables.
Yeah, so you have one left. Oh no, you have
Oh.
one left, but
Yes.
there's one left. Okay, so there are. Yes. And you can. By using those two things, you can know that B equals something times the linear combination of A and this. And then you can find out B for given A, you can find out B, C, D.
Yes.
Given A, you can find out B, C, D.
Yeah, also, you didn't use all the conditions, right? Because now if you fix A, B, C, D with one equation, 1 point only, what happens to the other point you cannot determine anymore?
Given A, and then you have to find out B, C, D.
这方程一定有解。
这是问题的一部分。
Well, you also.
Yeah, but you also want to solve this one, and you want to
Yes.
solve this one.
And the first one, you know that I think x1 should be 0.
No,
Okay.
x1, x. We're also in projective space, right? So they have relations.
Also those one.
Yeah.
Oh, it's hard. It's really tight.
Well,
你就不同的解析方程组是吗？
你就是用干性方程组。
you should solve it smartly. I mean, otherwise you're computing,
Okay.
forever, right?
拿题交给计算机。
可以交成计算机，或者是选一个简单的方法。人机法。Well, first of all. But you lose all the experience when you. It's all good. You see, it becomes computational problem. You have to solve a bunch of equations, right?
Yes.
Shall I just show you how to do that in a not too bad way? Okay. Oh, well. Did I erase it already? I found a very nice 2-line way to do this. Oh, well, I guess I have to do it this way. Okay. Okay, let's assume y1 and y2 is not 0, okay? So this point is now corresponds P1 is actually x1 over y1. And we want to map it to 0 with, yeah? And P2 is x2 over y2, and we want to map it to 1. Yeah? So now, how to do that? Let's call this thing x tilde 1, and this thing x tilde 2. And so you choose x, y, a tilde 1 plus b equals 0,
I got it.
and a x tilde plus b equals 1.
Okay.
Right? So that fixes your a and b.
Oh, so it's on this.
Yeah. So, and now you have 2 things left, c and d. And P3.
There's a one to one mapping from RP1 to infinity.
Yes. So either P3 is already infinity if y3 is 0, or it's not 0, then it's x3 over y3. And then what you do is, 3. Yeah. And then what you do is say, well, I want to map this to infinity, right? So I have to do something like this. X like this, right? And then normalize properly. And then when x equals this one, this will be mapped to infinity, right? And you'll have to normalize this properly. That is also still 0 and 1. Yeah? Yeah? So there's only one map. To do that. But the order is, of course, important because the map here will change, right? And I should write that a bit. The order map matters because the numbers here, A, B, C, D, C is 1 here. I can normalize one of those people. It will matter for these coefficients, which order I take, which one is mapped to 0, 1, and infinity. Okay? So now, when I have a 4th point, right? Then I can map these 3 to 0, 1, and infinity. This point will be mapped to something called M. And this is called cross ratio.
Now we know this matrix. We can use maybe x for y4 to times this matrix, and we know that what it is.
Exactly. So because this one determines a matrix, now I have a fixed point. So this map will be mapped to 1 point only.
Yeah.
And this thing, this number, which is in R, it can be infinity. Well, cannot be infinity because it's 4 different points. It's called the cross ratio. It's something called cross ratio. And that is actually, by definition, because we normalize everything to 0, 1, and infinity, a projective invariant. Okay? Now, why is this called cross ratio? Maybe you want to compute M. Okay? The reason why this thing is called cross ratio is because if you compute m, what happens? Assume P1 is 0, P2 is some S in R, okay? P3 is T in R, and oh well, probably it's by let's just call it P3. And then with P4 is infinity, okay? So my mapping the thing, this is already 0, right? This should be mapped to 1. This here should be mapped to m, and this here is already infinity. So what is m in this case? So the map is just I want a map that keeps my 0, keeps my infinity, and maps this s to 1, right? So my map looks like this, right? Yeah. So to which point, what is m? Yeah. Okay. So now let's make it more complicated. Sum S1, P2 equals S2, and P3 equals T. P4 is still infinity. How to now do the map such that this goes to 0, this going to 1, and this goes to m, this goes to infinity. Is m. Well, that's true because it's as you need to divide, x maps to s minus s1 to get this to be 0, and then you have to divide by s2 to normalize this thing to be 1. Okay, so this is correct. So m is in this case. Okay. So the last step is to replace infinity to be something finite. S3. How does that look like?
Over x minus 3.
In this case, m would be what?
S minus s1 over s2 times x minus s2.
Oh, just write it down for me. Can you write it down for me?
Okay.
You want to write it down for me?
Yes.
You know it? Yes, sure. Fine. Of course.
cross ratio 有中文的。
ratio 是比例的意思 ，cross 是对交叉比例。I think it's
Where is x?
x 被扔出去了。
应该是 m 那个 m equals that.
Is that this?
It's slightly more complex.
X maps to x times x minus x1 s1 over s2 x minus s3.
It's slightly more complicated. So how to get this one to infinity first? The multiple steps.
Over x minus s3.
So the first map is x maps to 1 over x minus s3. Right? Then we have this as infinity. And then we need to apply this one. Right? This map was x maps to x minus s1 over s2.
Yeah.
So we have
It should be x minus s1.
a composition of two maps, right? Now we want to say why is this a cross ratio, right? It's so you have to do this first and this as a second. So S tilde, when you do this, you change all these previous points with this, right? So that's the reason why you had the wrong result, because you forgot that when I map the thing to infinity, I change all these points. Yes. So it looks very complicated because it looks like this. So it's S1 minus S3, S2 minus S4, or T rather. Three minus ST. S1 minus S2. Okay? So why it is called cross ratio? Because you take the differences of these points pairwise and take the ratio of it. Okay, 1, 2, 3, 4. It's better if it's called TS4. You have 4 points. I mean, it's like they lie on the line, right? It's 1, 3, 2, 4. And then you take the ratio of that to the lines. It's 1, 2, 3, 4. It's called cross ratio because 1, 3, the segment between those, and the segment between 2 and 4. Wow. 反了? 3, 4, and 1, 2.
Okay. Yes.
You can change the 3.
Yeah, I guess I did something wrong here. Yes, it should be 3 and 4. And then it's correct. Exactly.
Yes, that's right. That's right.
So that's why it's called cross ratio, because you take the ratio between the cross and, okay?
简单粗暴。
Okay?
简单粗暴的交叉的比例。
对啊。
交叉比例。
Yeah. Okay? Good. So, it looks really horrible, yeah, because it's complicated, because projective geometry, after all, is not that easy. But it is a good invariant of your projective geometry. And this is the only thing that makes sense, in a sense, yeah? Because, why is it an invariant? Because there's only one map that maps 1 through 3 to 0, 1, infinity. This is uniquely determined, and then the fourth point follows. Okay? So that's why any arbitrary point I give you, 4, I can only compute basically up to order of 1 to infinity, 1m. Right? Of course, you can change the order, it will change m. Yeah? Yeah, because you can choose P1 to map to R1, P2 map to 0, P3 to infinity, it will change m. But there's only finitely many combinations. Okay? Now, one thing I wanted to say, m is a real number. Okay? If you do that, m is a real number. You can do that for complex numbers. All these things you can do with complex numbers as well. So you get CP1.
Yes.
Again, C stands for complex numbers, P for projective, 1 for dimension. And we know CP1 is just S2.
Yes. That's right.
Yes? No, you know or not?
I know.
So again, let me do the same computations. Z1, Z2 is equal to Z1 tilde, Z2 tilde, if there exists a lambda this time in C.
Yeah.
Lambda in C, right? With Z1, Z2 equals lambda, Z1 tilde, Z2 tilde. Right? So we are actually in C2 without 0, which is R4.
Yeah, it's awful. Yes.
Yeah? So 4 dimensions. We have that. Now, when the Z2 is non-zero, then I can map any of my point. I map to 1 over Z2, which is in C, a complex number.
So all of this can be mapped into C, but with positive infinity, and that's the Riemann surface.
That is S2, the round sphere, a plane with a point at infinity. Okay?
That's the Riemann surface.
Now, you can consider your RP2, or RP1, not RP2, RP1 sitting kind of in CP1 by just considering real numbers instead.
Yeah.
Right? Okay. So now, you can ask, what are projective transformations of your CP1? Same game as before. Same game as before, which is A, B, C, D with,
But that is SL2.
yes, that equals 1. So now A, B, C, D is not in R anymore, but in C. And this is a complex relation, so it's still 3 complex freedoms, okay? Yeah, 3 complex versus, so a complex number is nothing else but x plus I, y, and these are real numbers. You can write it as x comma y if you like, just like in the plane. So it's 4 dimensions.
R2.
2 times. So these are, each of these is xy. This is also xy. So it's 4 numbers. Okay. So you can do this. But again, RP1 sitting inside CP1. So when these are all real, I preserve my RP1. Okay. Now the question is, again, everything is in C, right?
Yeah.
Most of the CP1 is in C. Now the question is, what transformations A, B, C, D will preserve a circle? Oh, well, when will 4 points lie on a circle? When will 4 points in CP1 lie on a circle?
Oh, circle.
Okay? And that, because we don't running out of time, but that happens exactly when the cross ratio, as we defined before, is real.
Oh, yeah.
Because then all the 4 points lie on a line. And that is a circle in. Yeah? So that's how everything fits together. Okay? Good. I guess we stop here. I had a theorem for you, but I think we do that next time. You can look it up. It's called Pappus theorem. And the question is, why is it even a projective theorem? Okay? I've stated. Pappus. So it is known to ancient Greek. And the theorem is the follows. I have 2 lines, L1, L2. I have 3 points on this thing. And 3 other points arbitrary on this one. And let's see, do I have colors? Just 3 different colors. I combine A with B, B with A. I do B with C, C with B. And I do A with C and C with A. And I have 3 points. 1, 2, 3. And if I did everything right, and this thing is called the Pappos line. Okay? Arbitrary points. And the question is, why is this a projective geometry theorem? I mean, you can prove it. And probably if I give you a week of time, you will come up with an answer. But the question is, why is this a projective geometry theorem? And that we will do next time. 这个，因为这个 theorem 在一般的二维就可以写下来。
感觉特别像中学的几何。
对啊，
是我觉得见过非常类似的东西。
肯定是见过，肯定也很有名的。为什么这个很有名的原因就是很简单，可是 interpretation it's a matter of interpretation 为什么是对的？你要有个 proof， 可是这里还是没有回答这个为什么这个是这样的。
那证明它不就是这样吗？
不一定啊，你要懂这个证明，有和各种every theorem 随便一个什么定义啊，都有各种各样的证明，然后你问题就是为什么是对的，不只是可以证明。
然后它证明出来的不就是对的吗？
当然证明出来是对的呀，可是为什么是
那
为
本
什么？
质是什么？就是说我可以告诉你，从整个 R 上 e 的负 x 的平方 dx 它是根号派，那你就看本质是什么？它为什么？你可以一定算出来，你可以用多重的换元积分法算出来，但它为什么是对的？
OK，that's all。下课。